All right, so it is day 18 of Advent of Code 2022, and I am traveling again. So this is how we're going to do it today. Yep, let's dive right in. Uh, all right, day 18, boiling boulders. You and the elephants finally reach fresh air. You've emerged near the base of a large volcano that seems to be actively erupting. Let me just make sure. Yeah, okay. Fortunately, the lava seems to be flowing away from you and toward the ocean. Bits of lava are still being ejected towards you, so you're sheltering in the cavern exit a little longer. Outside the cave, you can see the lava landing in a pond and hear it loudly hissing as it solidifies. Depending on the specific compounds in the lava and speed at which it cools, it might be forming obsidian. The cooling rate should be based on the surface area of the lava droplets, so you take a quick scan of a droplet as it flies past you. This is your puzzle input. Because of how quickly the lava is moving, the scan isn't very good, its resolution is quite low, and as a result, it approximates the shape of the lava droplet with 1 by 1 by 1 cubes on a 3D grid, each given as its XYZ position. To approximate the surface area, count the number of sides of each cube that are not immediately connected to another cube. So if your scan were only two adjacent cubes like 111 and 211, each cube would have a single side covered and five sides exposed, a total surface area of 10 sides. And here's a slightly larger example. In the above example, after counting up all the sides that aren't connected to another cube, the total surface area is 64. What is the surface area of your scanned lava droplet? All right, so our input is a lot bigger, right? So I think thousands probably. Yeah, let's take a look at how we can attack this one. So I first, oh, this is awkward. Okay. Yeah, so the first challenge was finding out. So we have all the coordinates, and then I had to find out what would be the best way to model, the problem. How do I get the surfaces, and how do I use the coordinates? So what I ended up deciding was that the coordinate is if you imagine a three-dimensional coordinate system, the cube with coordinate 0.0.0 is the one that starts there and then goes 1 in each direction. So the diagonally opposite corner is going to be at 1.1.1. So that gives me like an idea about how do I understand where the blocks are, and then I needed to find a way to represent the surfaces so that they would so that I could map out or list or work out what all the surfaces were, and then find duplicates. And any duplicates would not be counted because that means that there are two blocks that are touching. So, oh no, got to switch back to this guy. Yeah, here we go. Okay, so part A, as usual, start by loading all the lines. For once, the input is very simple to parse. It's just the coordinates, so that's pretty straightforward. That's what we're doing here. So we create a couple of sets. So we have a set that has all the surfaces in it, and then we have one that has all the blocked surfaces. And a blocked surface is one that we've already seen once. So as we go through the list, and for each cube, we add all of its surfaces to the set. And if the same set occurs twice, that means that two blocks are touching, and one of that specific surface is not showing. Okay, so we go through all the lines. We get the coordinates like this. So from the inside, we start by splitting the line by commas, just for good measure. Yeah, sorry about the noise. Airport again. But yeah, just very simple. Integers separated by commas. So we get we split it by the commas. We apply int to what we get from there using map, and then we have to call list on it to get uh, to actually get the values from the map. And then we store the output of that into the XYZ variables. Okay, so the trick then, as I said, is to, given a cube, to find a way to return all the surfaces and then do all the set operations needed to make that work. So let's, yeah, I have some comments here that I needed to kind of work it out in my head. So the way that we represent the surfaces is it's a 4 tuple. So there's the XYZ coordinates, which represent the cube. And then the final element of the tuple is a letter, which can be, or a character, which can be either X, Y, or Z. Excuse me. And the one that is called X is the surface on the positive X side of this cube. So if you have the cube that starts at, I'm trying to show it with my hands because I don't have a whiteboard or anything here. So yeah, the cube has, obviously it has all the sides, but the one that is in the X direction is called X. The one in the Y direction is called Y. The one in the Z direction is called Z. And the other sides are then named according to like the adjacent cube, which would have a whiteboard would really help here. So if we have a cube here and this surface here is called X, then the cube that is right next to it, so the one that's right over here, its X surface is the one that's right here. So that corresponds to, I don't even know if you can see what I'm doing with my hands, but we'll just pretend. Yeah, we have our cube. X is this surface, and this surface right here is really, we call that the X surface of the cube that's over here instead. And once we have that, it all becomes pretty simple. So the way that we do that is, get cube surfaces. So we pass in the coordinates, and then obviously it has its own X, Y, and Z surfaces that are in like those 3 directions. And then to get the surface that's opposite X, we take X minus 1 YZ as that is the coordinates of the adjacent cube, and its X surface is then the same as our original one's opposite X. I hope that makes just a little bit of sense. But that's what this function here does. So it takes the input and then the input surface, and then it returns the identifier for all the surfaces of the cube. So we get all the surfaces here. If we have already seen that means that it is blocked, and then we add it to blocked surfaces. And if not, we add it to all surfaces, and we just keep going through, and that's really it. Then we just take the length of all surfaces minus blocked surfaces, which is these are set operations. So every element that is in Plucked surfaces gets removed from all surfaces, and the end result is all the surfaces that aren't blocked, and that was it. So, part B, part two, sorry. Something seems off about your calculation. The cooling rate depends on exterior surface area, but your calculation also included the surface area of air pockets trapped inside the lava droplet. Instead, consider only cube sides that could be reached by the water and steam as the lava droplet tumbles into the pond. The steam will expand to reach as much as possible, completely displacing any air on the outside of the lava droplet, but never expanding diagonally. In the larger example above, exactly 1 cube of air is trapped within the lava droplet at 2.2.5. So the exterior surface area of the lava droplet is 58. Yeah, so this one I was a little stumped. I kind of struggled to figure out. I thought the way to, that's the wrong way. Well, we can stay here. I thought the way to go was to, whenever I would place another cube, I would try to see if that sealed off, something else. I know that in the example there was just like a single cube that was air. But I didn't feel comfortable assuming that they would be individual ones. I kind of figured that with the big input, that there could be like larger areas inside of it that would be air, rather than just like individual little points. And then it was I couldn't work it out. But what I ended up doing was I realized that even though there are a lot of points, you can see the input, almost 3,000 points. They are all within a relatively small area, 20 by 20 by 20-ish, I think. I think those are the highest coordinates we see. Thereabouts, 20, 21 or so. I'm not exactly sure. But 20 by 20 by 20, that's only 8,000 cubes, which is perfectly reasonable to go through. So adjacent surface. Okay, let's see what we do here. So we have part B. Again, we get all the lines, and this bit here is pretty much the same. So we create a set of all the cube surfaces. We don't in this situation we don't really care about duplicates and whatever, because we're doing something else. Okay, then I create this neighbors array or list, which has the deltas that I need to apply to the coordinates of a given cube to find all of the ones, all the neighbors. So the first one will add 1 to the x coordinate. This one will add 1 to the y, z, subtract, blah, 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 blah. So, yep, that gives us all the ones. And then I get the minimum or the maximum, and then I subtract 1 and add 1 just to make sure that I don't start out in like a corner that I can't get out of. So I start by I create some sets, and I initialize the toVisit set to be at 0.0.0. That should have probably actually been min rather than 0, 0, 0. It worked out, but if I were doing this again, I would change these to the minimum, so that I'm -1, right? So I make sure that I don't end up in a situation where like the 0.0.0 cube happens to be surrounded, and then I can't go anywhere. Anyway, So we start by popping one off the set, and then we get all the neighbors using like this array up here. So that's the delta x, y, and z values. Then we calculate the neighbor. If we're already seeing it, move on. Otherwise, we add it to the scene. And if any of the coordinates yeah, right. So if any of the individual coordinates, so the x, y, or z, this is called x, but let's call there. Otherwise, it's a little it's not very obvious that this goes through. Neighbor is the coordinates of the given neighbor. So this will go through first the x coordinate, then the y coordinate, and the z coordinate finally, and then it's going to compare all of them to see if it's outside the bounds, and if it is, then we continue, then we don't care. If not, that means that oh, right, yeah. So cubes is the set that we created up here. So when we went through all of the input, right? So we created, a set that has all the cubes in it. And if one of these neighbors, we start from 0, right, and then we work our way out. And if any of if the neighbor that we're looking at right now, if it's not in cubes, that means that it is reachable, right? So we start somewhere, and then we go in all the directions, and if there isn't a cube there already, that means that it's reachable, and then we add it to the list of reachable, and we add it to visits, and then we keep going, and eventually that searches the entire area. And then we have then reachable contains every single point in the coordinate system that is reachable. So that is anywhere that this steam or water, whatever it is, can get to. And then we do kind of the same thing again. We get all the surfaces of those blocks, and we add them to a list of reachable surfaces, and then we so that those would be every single surface that anywhere that would be reachable, and then we get the intersection between those, and then all the actual surfaces of the actual cubes, and the length of that is the answer. And it's pretty fast this time. That's it. Yeah, I had to get up at 3 to get on this flight today, so I did not stay up last night to do this. Sadly, but I wanted to get this video out anyway. But yep, I think that pretty much covers everything here. There's nothing, like no cool algorithms out there that we're learning about. It's just following the instructions pretty much. And that's it. If I'm not moving around enough. Oh, sorry, I thought that was someone I knew. Yep, that's it. I hope the audio works at all. I didn't even check it. Yeah, it looks like it. Okay, but I hope this was helpful. And if you have any questions or comments, you know what to do right there. And if you like this, if this was useful, please like and subscribe. And I will, I'll see you tomorrow.